Hello and welcome to Special Factoring Formulas. Now there's 5 formulas, there's really only 3 formulas, but there's 5 formulas listed here that we're going to look at some special cases when it comes to factoring. So the first are the perfect square trinomials. And a perfect square trinomial means it can be written, it's a binomial, 2 terms, it's a perfect square. But when it multiplies out, it turns out to be a trinomial. So perfect square trinomials, whether it's an addition in between in the binomial or a subtraction, the only difference is right here, the addition or subtraction. So 2ab, so we have a squared, 2ab, b squared, a squared, 2ab, b squared. What are the signs? Same, always plus. All right, we have difference of squares. If we are subtracting 2 terms that are both squared, it factors as a plus b times a minus b. So a squared minus b squared always factors as a plus b times a minus b. I'm just going to write this here so it is not forgotten completely. The sum of squares is not factorable over the real numbers. If you want to know more about possibly factoring the sum of squares, look for a lecture on complex numbers. All right, and coming soon. So not factorable over the real. I promise I know how to spell real numbers. Okay, different squares works out, and these, write them down. Have them on a sheet of paper. Print out this section of notes for those of you that are my students. Put it on a note card, do whatever you need to do. Have these handy as we go through these examples. Now, here in the difference of cubes, a cubed minus b cubed, difference, subtraction of cubes, third power. So how do we factor it? Ignore the signs for now. We have a single a and a single b, so singles, and then pairs, AA, AB, BB. Those are the only 2 ways that we could put A and B together in pairs, and that will give us cubes. So we have singles, all the pairs give us the cubes. Here, a cubed plus b cubed, sum, addition of cubes. Singles, all pairs. Right, these are very similar, the AB and the 2AB, so make sure you're using the appropriate formula. Now, it's for the signs. So we're going to call this minus sign the start or initial. The plus sign is the initial. So this first sign is always the same. The second sign is always opposite of what we start with, right? The sum has a minus sign. The difference has an add sign. And let's make this one in green because we're just going to go for it. It's always plus at the end. So these formulas are so much the same that it's singles and then pairs to get the cubes. Same sign, opposite sign, always plus. Here we go. Let's factor some of these special formulas. Now I encourage you, when you have 2 terms, always look for a difference of squares or a sum of difference of cubes. I see 36 here, and I know that that is 6 squared. So once I have a difference, subtraction problem, using squares, I know this factors is x plus 6 times x minus 6, according to the rule at the top of this video. All right, that's it. We're done. We're finished. Now, it turns out that this 36, I just had a problem like that. I'm thinking, hey, look, it's 6 squared. All right. And what's 12? 12 is 2 times 6 times x. So if I wanted to force this idea of the perfect square trinomial, I see that I have squares on the ends, and it's 2, it's double, a 6, and an x. So it turns out that this works really well as x plus 6 all squared. But maybe you don't always necessarily see that. Keep in mind, we have other techniques of finding this as well. I want 2 things that multiply to be 36, add to be 12. It seems like 6 and 6 is the way to go. So x squared plus 12x plus 36 is x plus 6 times x plus 6, which is x plus 6 all squared. So if you had, like you have limited memory and you could only store a couple of things, the formulas still on the page are the ones that you should definitely memorize, more so than the perfect square trinomial. But, you know, every once in a while I'll throw one of those in just so we can check it out a little bit. Okay, I see two terms. So I'm thinking difference of squares or sum and difference of cubes. It's a difference. A is squared, b is squared, but let's check the numbers. Oh, look at that. 16 is 4 squared. So 4a all squared minus, see, 81 is a perfect square. That's 9. B squared is a perfect square. If I rewrite this 16a squared minus 81b squared as 4a all squared minus 9b all squared, I'll end up with a factored form of 4a plus 9b times 4a minus 9b. Now, it doesn't matter which order you put these in. They're being multiplied. You could multiply in either order. I like to be a positive person, so I always put the positive one first. But it doesn't matter. It doesn't matter at all. Here we have m squared plus 25. So there's two terms. It is a sum, and these are squares. And we cannot factor the sum of squares over the real numbers, and so we call that prime. A polynomial is prime if it cannot be factored over the real numbers. All right, prime. Let's try a few more examples. Now I'm looking at this 36a squared minus 60a plus 25, and I'm thinking to myself, I have to multiply 36 times 25, find the answer, and find things that are different by 60? Oh, that seems horrible. But then I notice, hey, look at that. That's 6a all squared. It's 25, that's 5 all squared. So I'm really hoping, is this minus 2 times 6a times 5? Well, 5 times 6 is 30, times 2 is 60, and minus 6a. So if it's a really horrible number, I might start looking, hey, look, I have some squares. Let's see if this middle term works out. And now that I have that, I can factor it as 6a. The sign of the middle term tells us what it is, minus 5, all squared. And you just save yourself a ton of time in not having to factor 36 quarters. Let me see. So these are 4, 9, 900. I don't want to write all the factors for 900. That's crazy. Now I'm curious. Let's see how my mental math skills are. Let's do the correct operation. 900. Awesome. Okay. Moving on. I always have to keep my mental math skills up. Do as much mental math as you can to keep your brain healthy and active into your older age. So I'm looking at a sum. Okay, I'm scared. All right, maybe it's a sum of squares again. Maybe I'm not squared. Maybe I'm not squared, really? Maybe I'm not scared because that means I don't have to factor it. But then I see, cubes. All right, x cubed plus 2 cubed. So what is it that we're cubing? We're cubing x and we're cubing 2. So x and 2, those are the singles. And then we take them in pairs. X times itself, 2 times x, and 2 times 2. And then the pattern is the same, opposite, always plus. And the super cool thing is the trinomial, 3 terms, trinomial, in parentheses, almost never factors. And I only say that word almost because I'm sure somebody could give me an example where that part's going to factor. Actually, nope. I was going to say I just thought of an example, but it's very rarely. Okay, so moving on to number 7. I'm going to scroll up a little bit here. X cubed minus 27y cubed. What is it that we're cubing? We're cubing x. See, 27. 27 is 3 times 9. 9 is 3 times 3. Oh, yeah. 27 is 3 cubed. So if I want 27y to the third power, I can use 3y and cube it. This is kind of the opposite of what we were doing if you watched my earlier video on rules of exponents. So now we have our terms. So we have the singles, x and 3y, x times x, x times 3y, that's 3xy, and 3y times 3y is 9y squared, right? Double, right? 3y times 3y. The signs are the same, opposite, always plus. Same, opposite, always plus. 16m squared minus 56mn plus 49n squared. I'm thinking about a greatest common factor. No. I'm thinking about not even variables. I'm thinking, do I really want to multiply 16 times 49? I hope not. That's 4m and all squared, and 49n squared is 7n all squared. So I'm hoping this is, let me see, I'm just going to write what it needs to be. And see, 4 times 7 is 28. 28 times 2 is 56. So we know this will factor as 4m, the sign of the middle term, the last. All squared. And you could verify that by multiplying it out if you wanted to, or you could do the 16 times 49, find all the factors, and find the ones that are different, or add to be 56. Ain't nobody got time for that. Okay. I certainly don't have time for that. So sometimes the perfect square trinomial comes in handy. Number 9. I like to give plenty of examples with these formulas because it seems like it's just magic when you see somebody do it and you're like, that's it. So plenty of time so we can watch it develop. I'm looking at 250a cubed minus 16b cubed. I'm thinking cubes. But as I look at my cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. There's no 16, right? 16 is not a perfect cube. 250 is not a perfect cube. You see, what do we have? 4 cubed is 64. 5 cubed is 125. 6, we could keep going, right? But I'm not going to find these as perfect cubes, and so I start scratching my head, and then I remember that we always have to start with a GCF. All right, I like to throw one of these in just kind of unexpectedly in my examples as a reminder that we've always got to be looking for a GCF, and I see that 250 and 16 are both even numbers, so I'm going to start there. 250 divided by 2 is 125, and I still have the a to the third. Horrible looking 3. Minus 16 divided by 2 is 8, b to the third. And that's when I notice, hey, now I have cubes. Fantastic. So this factors as we're going to have the 2, and then 125a cubed. That's 5a all cubed, 2b all cubed minus sign. So I have the 2 on the outside, and then I'll have 5a and 2b just as individuals, and then I'll have 5a multiplied by itself, which is 25a squared. I'll have 5a times 2b, and that's 10ab, and then I'll have 2b times itself. 2b times 2b is 4b squared. I was going to make a Romeo and Juliet joke, and then I decided I should stick to math. Subtraction, so it's same, opposite, always plus. And we have completely factored this. First factoring out the GCF, and then using our difference of cubes formula. All right, last one. Last one, m to the fourth minus 16. Well, we don't have a difference of fourth power formula. So how could we think of this as squares? M squared all squared minus 4 squared is the same as m to the 4th minus 16, right? We have to be able to take apart these powers sometimes as well. Fantastic. This is just a, quote, a simple difference of squares. So this is m squared plus 4 times m squared minus 4. And with this sum and difference of cubes formula, I said, look, this part's never going to factor. Like almost never. I had to qualify it, but I'm pretty sure it's never. Here, we don't always have that. So I noticed that I have a sum of squares, so that's got to stay. I can't factor that anymore. But notice this is a difference of squares, yet again. And if this is a difference of squares, what are they? They are m all squared minus 2 all squared. So I'll have m plus 2 times m minus 2. And we have completely factored what looks like it's a subtraction of 4th powers, and it is. But we factored it as the difference of squares twice. All right, so difference of squares, sum and difference of cubes. Keep those formulas in mind, and I'm not going to lie. Perfect square trinomials, pretty handy to have that formula instead of having to use our AC method of factoring. Well, that's it for the special topics, special factoring formulas. Thanks for listening.